The floor is yours.
Well, now we have very few minutes for the presentation. Okay, so I'll make a quick introduction of who we are for the people who don't know Xinnor, and then I will leave it to Daniel to explain the topic of our presentation, how to make best practice for all-flash multi-node high availability. So for the people who don't know Xinnor, Xinnor is a small startup. We are 3 years old now, but in reality, our technology is older than that. You heard in the presentation of Daniel, he has been working on NVMe RAID since 2015. So it's quite some time that we have been developing this technology under a different hat. The mission, our focus is to provide the fastest RAID engine in the market. I see those are the previous slides, not the latest. Okay, is there any way to switch or? Sorry about that. But I can carry on in the meantime, maybe while you switch the slide for Daniel. Okay. So we're a small team. We're about 50 people. But if you think about that, we just do RAID engine for NVMe. We're probably the largest team in the world to do that. We're still a young company, recently founded, but we already have quite sizable business for us. So we already have over 100 petabytes of all-flash under management with our software. And this quarter, we're growing fast. This quarter, we deployed another 30 petabytes at multiple universities. Universities is, yeah, that's the one. The universities are now our primary focus because they are the early adopters of high-performance computing, AI type of technology. Some recognition, we work with many partners, but the main recognition we are mostly proud of is we achieved second position in the IO 500 for 10 client research, and we're now working on getting to the first spot with a real deployment, so it won't be 10 client research any longer. So effectively, what we do is a software RAID. So what we do, we take NVMe drives, we create a RAID group, and we expose it as a block device, and then you can mount the file system on top. The secret sauce of our technology is made of two fundamental components. One is the way we use vectorization. We use AVX technology in our Z-RAID classic implementation, and the way we combine it with our lockless data path. What does it mean? It means that we can dynamically allocate the stripe to the available core of the CPU. And by doing that, we avoid spike of load on a specific core, which is the main problem on all the other RAID implementation in the market. So by doing that, we distribute the load, we avoid spike, and we can maximize performance. So if you will have the chance to test it, and please apply for a trial. You can get free trials to play with our technology. You will see that we normally show much higher performance than any alternative in normal operation, predominantly when it comes to write operation and random read and random write. Equally important, you want to have RAID because you're afraid that a drive at some point will fail. When it fails, we are able to keep performance very close to the normal operation performance. So that's a main differentiation versus alternative technology. Software only, no need for any GPU to run our software. And we support many different type of RAID level, including 3 drives parity or including up to 32 drives for parity over 64. And then we support many features. Actually, the main one for today is about the integration with pacemaker and chorusing to enable clusterization. Over to Daniel.
Yeah, thank you very much, Davide. Sorry. Well, first of all, my next speech will not be about how fast we are, because, well, we have a lot of partners which we work with on different projects on Lustre, Lustre configurations, installations in different cases in universities and in other companies. So I would like to share with you our vision and our experience in what high availability architecture can be considered in different cases. And I think it is not really related to us, because we have competitors. We have MD-RAID, which works quite good in some situations, and it declares support for pacemaker. Basically, it should work about this in the same manner as we work. And also, we for sure know that we have ZFS, which also can be integrated with pacemaker cluster. And all the following things I will tell you is about how we see, what we see as an optimal architecture of pacemaker cluster for Lustre. We work quite close to the hardware, and that's why I will talk mostly about some hardware components and some topologies of NVMe sharing between the servers. So first of all, let's take a look at the very basic basis of the high availability clustering. What high availability clustering should provide us? It should provide us service continuity in case of a server failure. To be honest, it should provide us service continuity not only in case of server failure, but any other component failure. It's better to have continuity. And also, which is not required, but it's better to have, is to continue to work with the same speed in the failover state, because you can survive the failover, but if you slow down your performance after the failover, it can be a problem. Some cases, some installations, some customers are okay with it. Some not so okay. So different solutions for different cases. If we will take a look at the current Lustre public available documentation, we will see that the standard Lustre approach for the clustering is based on failover pairs, or basically dual node clusters. The failover pairs can be active-passive or active-active. In most cases, it is for sure active-active, because on most time all the servers are working okay. And why should be not using the server resources of the passive node? But in fact, how this failover pair is built? These nodes are combined with pacemaker cluster with some fencing, and they have a shared storage. In case of classical storage, it usually was LANs received from Sun, maybe with some SCSI-3 reservation, maybe without, and so on. But in case of NVMEs, usually we share just a set of drives, and some software engine combines them into a RAID on a Lustre node. Basically, this is how we work, and all other software RAID engines which we discussed before also. So the failover pair performance. In case of if we had an active-passive failover pair, a single server failure doesn't affect the performance, but it is 50% of redundancy. It's too much. That's why in most cases nobody uses it. And in most cases, in case of failover pair, if a node fails, then the performance of this pair degrades. Theoretically, you may over-provision in all the nodes You may increase the amount of CPU power 2 times, about 2 times amount of RAM, 2 times amount of drive connection throughput, about 2 times net connection. Anyway, you will still have about 50% redundancy, which is not good. It increases the system price, yeah. And also, if we have a Lustre file system combined from such failover pairs, a single server failure will lead to the pair performance degradation in case if we don't have such over-provisioning or 50%. So, but we know how the Lustre works. It distributes files, it stripes files. So in this case, all the file system performance may degrade. So it can be quite important problem for some customers. For some customers, it's okay. They understand that this is expected performance and they can live with it. So now let's go into the technical details, how the access to NVMe drives can be shared. The main technology now is basically NVMe dual-ported drives. Most of the NVMe drives now are connected to server by 4 PCI Express lines. And some of them, not most of them, but maybe 50% on the market, maybe 70% of the market, may work in the 2x2 mode. Basically, they work in dual port mode, and each port consists of 2 PCI Express lines, and you may connect one port to one server and another port to another one. These drives can be installed in specific devices, which we will take a look a little bit later. So here we talk about direct connection of dual port devices, or, for example, using devices like eBOF, which allows servers connect to the drives by network protocol, which is the main standard for now, is NVMe OFF by RDMA or TCP. So there are two options. I think the main, the system, the architecture of choice for most of our project, by our experience, now is storage bridge-based systems. What are the storage bridge-based systems? Basically, it's a box, usually 2-unit box, which integrates 2 servers and some set of drives, usually 24. Sometimes we know that some models exist with 36 drives. And each drive in this box is connected to each server by 2 PCI Express lines. So drives work in dual port mode. These boxes usually have internal interconnect between the servers, which makes them quite useful in to do pacemaker clustering. The internal link can be used for pacemaker interconnect. So each server has access to all the drives, and they all, for sure, they have IPMI. So you may arrange a fencing using IPMI fencing, and so on. It is not all the vendors provide such devices, but at least 3 vendors provide. It's Celestica, Supermicro, and Viking. We tested, I think, nearly all of them. They work quite good. But what is the problem here? The problem is that each drive is connected to each server only by 2 PCI Express lines. And to have the full performance of the drive, you need to utilize this drive by 2 lines from each server in the same time. Otherwise, you will have only about half of the performance of all the drives, because they initially was designed to work by 4 lines. So you can use a life hack here, just delete all the namespaces on these NVMe drives and create, instead of 1 namespace, 2 namespaces, and utilize first namespaces for RAIDs running on the first server And second namespaces use in another RAIDs on another node. In this case, each server will work, and it will generate workload to each NVMe, utilizing all the ports, all the PCI Express connection for each drive. Problems here, you increasing the number of Lustre OSDs in this configuration, which in some configurations may be a problem, and also in case of failover, it doesn't work. In case of failover, the survived node still will see all the namespaces. It's not a problem, but the connection will be just only by 2 PCI Express lines for each drive. So looks like SBB is not an option for the configurations where you need to have good performance in case of the failover. But it has a lot of advantages. It is quite simple solution. It is just a 2-unit box which you install in your rack. It has a very small data center footprint in the rack footprint. It has quite low, in comparison with our other solutions, power consumption. And drives are directly connected to the server, so you don't have additional latencies and so on. The problems an SBB system is still specialized hardware. Additional NVMe configuration required to get the full NV performance, I mean namespace configuration. And also, if you are paranoid, you may be afraid of the situation that when a passive hardware within SBB, like backplane, which is passive hardware, but it is a single point of failure, may fail, and you will lose the whole SBB system. So alternatively, how you may share the drives among multiple servers is above technology, where you have a separate box, which may looks like quite similar to SBB system. It is also provided by multiple vendors. It is a box which contains 24 or 36 drives, up to 24. Usually, it contains 2 independent I/O modules for high availability. Each I/O module usually uses 3 to 6 network interfaces, and network speed for this network interfaces are usually 100 or 200 gigabits per port, which, to be honest, is not so fast for modern requirements. Anyway, it is what we have on the market now. So in this case, we can build a configuration. We can have 2 servers, regular servers, nothing interesting. We will need 2 switches to have high availability, because in case of, if we will have only 1 switch to connect above, it will be a single point of failure. And we will have 1 or n eBOFs to connect to 1 or multiple server failover pairs. On the picture you see here only 1 failover pair, but in fact, if you have multiple eBOFs, then you may use multiple failover pairs, because you have too much NVMEs, and to utilize the full performance, you need a lot of network throughput in the backend to the drives connection, and also for LNet also. But let's calculate what we have here. A single server is 1 or 2 unit device, so we have 2 of them, so 2 or 4 units for servers, 2 units for switches. Okay, they can be used by multiple eBOFs, but 2 switches, and usually 2 units for each eBOF. It is not maybe so, well, it occupies much more space in the rack, and also it will consume more electricity in comparison with SBB. So, but it is much more generally available hardware, even eBOFs. No additional NVMe configuration needed because in this case, you may over-provision in a server with additional network cards to saturate the performance of the application in case of the failover. You don't have a hard limit of the number of NVMe drives used in this configuration because in case of SBB, you can't use more than 24 drives, but in this case, you can utilize more. Anyway, you need to create a redundant network for eBOF to server connection. You need to, and in comparison with SBB, it is increased complexity of the solution. You have more elements to administrate and more data center footprint, more consumption, and so on. And so, and once again, if we don't want a system to be and if we don't want a system to be to degrade of performance in case of the failover, we need to provision the nodes. What can we also do? Because eBOF itself, it is highly protected hardware. It has 2 I/O modules, and all the hardware within also is duplicated or is a passive. But in theory, you may lose the eBOF. For example, in case, once again, in case of backplane failure, sometimes it happens. What can be done? So, as I said, yeah, this is one of the vendor's eBOFs. You see its front, you see 24 drives. In the backend, you see a lot of, you see 2 I/O modules, I/O module A, I/O module B, and you see the ports to connect, you see ports to administrate, and so on. Not so very important. I think most of you saw these devices. If we have multiple eBOFs, and when we create a RAID, if we will properly select the drives from each eBOF, we can create a configuration when each RAID will be distributed among all the eBOFs or multiple eBOFs. And in the case of the eBOF failure, the RAID will not be lost. It will just lose some number of drives. So the general rule here, for example, if you use RAID 5 in this case, please don't use just 1 drive from each eBOF. If you use RAID 6, please use 1 or 2 drives from each eBOF. And in this case, if eBOF will fail, each RAID will lose, RAID 6 will lose up to 2 drives. And in this case, the RAID will still be available for you. At some moment, we had a question why we are stuck with failover pairs. Because in case of basically pacemaker and crossing, cluster limit is, depending on the version, is 16 or 32 cluster nodes. And using eBOF technology, you will share the same drives among a large number of servers in the same time. It is not a problem. And we had a chance to create a configuration and test this configuration with, at this time, only 3 nodes. But I think we will be able to reproduce these tests with a larger number of nodes. A partner provided us an environment. He provided us eBOF with 24 drives, but he split these drives into 2 namespaces to provide us more drives. And we wanted it to create a complex configuration. So we created a complex configuration of 3 nodes. We run the 8 OSTs and 3 MDTs. So we clustered it. The MKFS Lustre file system worked with service node parameters for 3 nodes perfectly. Mounting was perfectly, so no problems was found here. And we believe that this architecture could somehow help us solving the main problem. But when working with multi-node cluster with eBOS, basically we have two options: non-dedicated redundant nodes and dedicated redundant nodes. Non-dedicated redundant nodes is the configuration which I showed you before, which we made experiments with. This is the configuration. For example, we have 4 servers, we have some set of eBOFs, we have MDTs, OSTs, and so on. In case of failover, in case of server failure, the services moves to one of the nodes, or maybe it will be distributed. In this picture, you see that all the resources are moved to one node, but in real life, most probably Pacemaker will properly distribute the services among all the other nodes. And in this case, I am not expecting the degradation of the performance in 50%, but we will still have some degradation. In case if we have additional, just in this example, single redundant node, or we can have multiple redundant nodes, which are basically not a huge level of redundancy. It is not 50% at all. Yeah, for example, you have here 4 nodes which are perfectly sized to run their workload. And you add 1 node which was of the configuration of most resource demanding node. Basically, most probably it will be about just the redundancy level will be just 1/4 of all the resources. And in this case, if a node will fail, all the resources from this node will be moved to the redundant node. And looks like no performance degradation will happen after the failover. So this was the idea. So you can build it on generally available hardware. You don't need, in comparison with SBB, no additional NVMe configuration needed to get full performance for the drives. No need to split them. No hard limit number of NVMEs used in the configuration, and low redundancy level. You don't pay too much for this redundancy. No performance degradation in case of a server failure. Disadvantages: you need a redundant network for eBOFs, and in comparison with SBB system, nothing can compare in terms of simplicity. This configuration is more complex. Basically, that's all what I wanted to tell you.
Any questions for Xinnor? No? Okay. Thank you.
Okay, let us